Now we are going to study ionic compounds. So reactions, first of all, we are going to learn reactions of metals with non-metals. So what happens when a metallic compound and a non-metallic compound combine together? So metals and non-metals, they combine together, react together with each other to form ionic compounds. So reactivity of elements can be explained on the basis of their tendency to attain a completely filled valence shell. That is, it means, so how can we determine if the reactivity of an element? So how many valence shell, how many electrons are present in the valence shell of that particular element determines the reactivity of that element. So valence shell is the last shell. So suppose there is an element, it has so this is the valence shell, and suppose it has one electron in it. So this will determine the reactivity of the element. As compared to non-metals, metals have few electrons in their outer shells and they want to lose their electrons to attain a filled valence shell. So suppose this KLM. So suppose this shell is completely filled, this is completely filled and it has one electron in this. So instead of attaining 7 more electrons, it will try to lose this one electron. So this is a tendency of metals to lose that one electron, or most of the time they have lesser number of electrons in their valence shell, so that to become more stable they will lose their electron. And whereas as compared to metals, non-metals will try to gain that electron in order to become more stable. So as I told you earlier, non-metals want to gain electrons to attain a fully filled valence shell. As a result, metals lose electrons. So suppose the metal has lost that one electron present in its valence shell. So now it will form a cation which combines with the anions from non-metals, and these cation and anion together will form an ionic bond as shown in this figure. So suppose this is the K shell of sodium. It has valency of 2 electrons. It has capacity of holding 2 electrons. It is completely filled. Now the L shell, it has capacity to hold 8 electrons and it is again completely filled. The M shell, it has capacity to hold 8, whereas it is containing only 1, whereas in this case 2, and in the outermost the L shell, it has 7 electrons in it. Instead of losing 7 electrons, it will try to gain 1 electron so as to become more stable. Now, gain and loss of electrons to form ionic bonds. So, suppose as we saw in the previous example, sodium has 1 electron in its valence shell, whereas while chlorine or fluorine, they are of same family, so they'll always have 7 7 electrons in their outermost shell. So sodium loses an electron to chlorine and becomes a sodium cation. So it will become Na plus. It is donating one. It is losing its 1 electron, so it will become a cation, that is Na plus with a plus sign. The chlorine anion now opposite attracts each other. So the chlorine anion is attracted to the sodium cation and an ionic bond is formed, which gives us NaCl. So the chlorine will gain one more electron and it will form Cl minus. Now Na plus Cl minus produces NaCl. So this is the how the electrons are present in sodium 281. Sodium in the periodic element, the sodium has 11 number. So it has 281 this configuration, whereas Cl is 17 number. So it has this configuration 287. So as I explained earlier, so this is how the sodium cation, this is how a sodium cation is formed, and chlorine anion. Chlorine anion is formed. So now these two will combine together. This is electron dot structure of chlorine. So it has 1, 2, 3, 4, 5, 6 and 7. 7 electrons in its valence shell, and it has 1 electron in its valence shell. So this is the electron dot structure of chlorine. Now electronic configurations of some common elements which you will be needing in the future. So first of all, neon. Neon is a stable metal. It is, it comes under the noble gases. So it has completely filled shells. It has no electrons in its valence shell. So it is completely filled. So it is stable. Whereas sodium, it has 2 electrons in its K shell, 8 electrons in its L shell and 1 in its M shell. So it will have a tendency to lose this 1 electron. In magnesium, it has 2, 8 and 2 in its M shell. Similarly, in the case of aluminium, it's 30 electronic number. It is 12 number. So it will have 3 electrons in its valence shell. Carbon, it has 2 in its K shell and in its L shell it has 4 number of electrons. So it will be needing 4 more electrons to be stable, to become stable. Nitrogen, it will be needing 3 electrons to become stable. Oxygen, it will be needing 2 electrons to become stable. Chlorine, we saw in the previous example, it will be needing 1 electron to become stable. Now, physical properties of ionic compounds. Let us understand the physical properties of ionic compounds with an example of an experiment. So, now let us take example of sodium chloride. Sodium chloride, potassium iodide, Ki, and barium chloride, or any other salt can be taken. So now we have to see what is the physical state of these compounds. So the physical nature of ionic compounds, these all are ionic compounds. As you can see, sodium is a metal, chlorine is a non-metal, potassium is a metal, iodine is a non-metal. Same in the case of barium chloride. So what is the physical structure of these ionic compounds? So these all are ionic compounds are solids and they are somewhat hard because the bond between these non-metal and metallic compounds, they are tightly held by electrostatic forces. So the bond between them is, a very strong force. So these compounds are generally brittle in nature, and they can be broken down into pieces when a pressure is applied on them. Now take a small amount of this sample and on a metallic spatula. This is a metallic spatula. Now take a small sample of one of these sample on this spatula and heat directly it on the flame. So now what did you observe? So the melting and boiling point of ionic compounds are very high. So this is because, as I told you earlier, they are held by strong forces, electrostatic forces. So this is because a considerable amount of energy is required to break the interionic attraction between these compounds. So this will not melt easily. These compounds will not melt easily. Now here, so now we have to check, do these compounds melt? As I told you earlier, they won't melt easily. Now we have to try to dissolve these samples in water, petrol or kerosene. So these electrovalent solutions, these compounds are generally soluble in water, but they are insoluble in solvents such as petrol or kerosene. So they won't be soluble in petrol or kerosene, whereas now let us take example of water. So suppose these substances are dissolved in water, and now we have to see if whether the bulb will glow or not. So we have to check the conduction of electricity. So a solution of an ionic compound in water contains free ions, which moves opposite to the electrodes when electricity is passed through the solution. So let me explain it in a simpler language. So suppose these ionic compounds are dissolved in water. So this will conduct electricity only and only when they are freely moving. That is, whenever they are dissolved in water and freely moving, only then they can conduct electricity. In their solid form, they won't conduct electricity. Now, as I told you earlier, they are held tightly with electrostatic forces. The intermolecular forces between these ionic compounds are very strong. So they have very high melting and boiling points. Suppose NaCl, it has 1074 Kelvin melting point and 1686 Kelvin boiling point. So this is a table. You can have a look at this to see the melting and boiling point of the following compounds. Now, properties of ionic compounds. First of all, we'll start with physical nature. So, as discussed in the activity, ionic compounds are generally hard solids. I told you the reason in the previous slide. This is because of the strong force of attraction between positive and negative ions. As the ionic compounds are nothing but the combination of positive and negative ions, so they are usually brittle in nature, but opposite attract each other, so they are very tightly held, or you can say they have very strong intermolecular forces. They have high melting and boiling points. So a lot of energy is required to break the strong ionic attraction. We saw in the previous table that like how much how much temperature is required to melt the NaCl, LiCl and other some compounds. So this is only because a lot of energy is required. Solubility. As I told you in that activity, they are generally soluble in water but not in solvents like kerosene or petrol. So this ionic solid is present in the solid state, and an experiment is being performed in this. So when the water is added and it is dissolved in water, now it is completely dissolved in water. Now a power supply is provided. The bulb will glow in this case. Whereas when it was in the solid form and the electricity is provided, DC power supply is provided, the bulb doesn't glow. So this means that the ionic solid will only and only conduct electricity when it is present in the form of solution, that is when it is dissolved in water, or which means that the ions are freely moving in water. So, with that video, we can infer the conduction of electricity of those ionic compounds. Now, I have already told you that ionic compounds do not conduct in the solid state because those ions are fixed in their position. As you can see, there's a particular lattice structure and it is fixed. So it won't conduct the electricity, but in the molten state, ions are free to move. They are freely movable in the solution, and then those compounds can conduct electricity. Now I have a question for you. Write the electron dot structure for sodium, oxygen and magnesium. Let's start with sodium. I told you its number is 11, so it's 281. There will only be one electron present at the top of Na. Now we have oxygen. Its number is 8, so it will be represented as 2 and 6. So as it has 6 electrons in its valence shell, so we'll represent it as 1, 2, 3, 4, 5, 6. So this is the electron dot structure of oxygen. Now we have magnesium. Its number is 12. So how can we write it? 2, 8, 2. So there are 2 electrons present in its valence shell. So it can be represented as Now we have to show the formation of Na2O and MgO by the transfer of electrons. So I'll start with the configuration of Na. It has one electron in its valence shell. Atomic number of oxygen is 8. It can be written as, it has 6 valence electrons in its valence shell. So now during the bond formation, electron Na will lose its electron to form Na plus, whereas it has to gain 2 electrons. So as to balance our chemical equation, we'll take 2 molecules of Na so that it can lose 2 electrons. Now we have 2 cations of Na. Now it has to gain 2 electrons, so it will become O minus 2. This is an ion and this is cation. So now these two will combine together to form Na2O. Now you must have observed the ionic compounds present in these ionic ions present in these compounds. So here we have this cation and this anion. Now we have MgO. So Mg, it is 12 282, oxygen it is 286. Now Mg, it will lose 2 electrons as it has 2 electrons in its valence shell. So it will become Mg2 plus, whereas oxygen, I told you how, it has to gain 2 electrons so as to become this anion. Now these two will combine together. We don't have to balance it as magnesium is already losing 2 ions and oxygen has to gain 2 electrons, so it will become MgO. Now why do ionic compounds have high melting points? So we discussed in the previous slide, ionic compounds are held together by electrostatic forces. When a positive and negative are combined together, they are held together by electrostatic forces between the oppositely charged ions. These forces, this is generally referred as ionic bonding. As the lattice contains large number of ions, so a lot of energy is needed to overcome this ionic bonding. So ionic compounds have high melting points.